and just on one topic and with one specific application in mind. So please bear with me if I'm getting into a little bit detail, but also remind me if I do not speak loud enough or I do not write big enough. So my topic is study of the fractional Laplace operator. Okay, so when gamma is a fractional number. So first, on flat domain, specifically on Rn, P is an operator we denote by P2 gamma F is just defined to be a Laplace operator to X gamma in X variable to the gamma power. So, and we would like to study this operator as a boundary operator of a function defined on upper half space. And this work was done on by Conformally and M.Zworski on this upper half space. Okay, so we like to think about this as a boundary operator of some equation defined on upper half space. Here is a classical setting. Suppose we study this Laplace operator, so this is Laplace both in X and Y, on 0 on the upper half space. And if we know U restrict to Rn equal to F on F, then the classical theory says we know what is this Laplace X to the 1/2 power F. Okay, so my minus Laplace is a positive operator. So the classical theory says this is nothing but, in some sense, the Dirichlet normal operator du dy at the point y0, x0. That y tends to 0, so that's this. So here is a quick way to see it. And to see it, we consider TF. T now is a function operator defined on Rn. And think about TFX is equal to minus uy restrict to Rn. And then we have a T square operating twice. And then you have a uyy. Okay. So this is equal to uyy. Restrict to the boundary. But our function u is harmonic, so this is the same as equal to minus Laplace x f u restrict to Rn. Okay, so it's Laplace u and in x variable, and that's equal to uyy, that's equal to 0. And u restrict to the boundary is equal to f, so that's equal to f. Okay. And that shows that this is equal to this Laplace x f. I'm sorry. So this shows this 1/2 is equal to this. And in a paper by Conformally and M.Zworski, in 2006, they extended theorem. Yes?
Well, I'm sorry, could you maybe write the subscripts a little bigger? Because you at the back were having.
Oh, okay. So I need to write a bigger. So, so their theorem is this. They consider, is this big enough? Laplace A, is that big enough? So it's Laplace U A, that's defined to be y to the minus a power divergence of ya, and now gradient in both x and y variable u equal to 0. So there is a weight a there. And then if one write down this operator, this is the same as equal to Laplace in both x and y plus a of y and b dy. So consider a function defined on upper Hell space satisfied Laplace au equal to 0. So this is u equal to 0 on upper Hell space. Then they claim that if u restrict to the boundary is equal to f, look at this weighted Laplace operator, and then if a is the index 1 minus 2 gamma, and if gamma is between 1 and 0, and i.e. this is the same as say a is between 1 and minus 1 for this weight, then I identify this boundary of y, Laplace x to the gamma power f is equal to some constant n gamma, and then limit y tends to 0, ya, y. So when a equal to 0, and when gamma equal to 1/2, that reduced to the classical theorem. Okay, so that's this theorem. And the way they see this is through so-called extension theorem. So this is implied by extension theorem. And the extension theorem is they identify the energy of this operator is Laplace to the fractional power minus Laplace x gamma f inner product with f of dx. They identify the energy on the boundary to the energy in the inside. There's a constant I do not specify. So through this, then they look at the boundary expansion of this and identify that. Okay, so that's the extension theorem. And they also apply this extension theorem and fractional power operator to the study of free boundary value problems. So in the meanwhile, we also know, looking at this theorem, our question is, that reminds us that on conformal geometry, we also have a fractional GJMS operator, and which in the special case of Euclidean space is this Laplace to the gamma power. So in conformal geometry, there's this GJMS operator. Okay, and then this GJM, the important property of this GJMS operator is the conformal covariant property. So this family of P2 gamma operator, and this P2 gamma operator has leading symbol the same as Laplace to the gamma power, but it is lower order term. And the important thing of this operator is this is a class of conformal covariant operator. And what does that mean? That means that this operator say, suppose we will talk about conformal geometry. So given a function g, say this is M1G, on M1G. And if we look at G of
Can you write Roger?
okay, E to WG, then this operator has the following property. P2 gamma of GW operating on any function phi is the weight of P2 gamma G operating on a weighted space of this function. And this is each time I need to think about this. This is n minus 2 gamma over 2 w times phi, and then exponential n plus 2 gamma over 2 w. And this is for every phi, say smooth function of the manifold. So this is the conformal covariant property. And this operator exists when 2 gamma is less than equal to n, when n is odd. When n is even, it exists for all order. Okay, so this is for 2 gamma between n and 0. And for example, the case when gamma is an integer, this is well studied, P2. P2 is the conformal Laplace operator. So this is minus Laplace plus scalar curvature times a constant. So this for operator G is G and G. And this constant is very specific. Nobody pays attention to it until the work of Paramount. Paramount that n tends to infinity and study the corresponding operator. So this is the conformal Laplace operator. And then there is also the P1 operator. And that's when gamma equal to 1/2. And this is the well-known operator, the boundary operator, which corresponds to the boundary operator of this P2. So it's minus KD normal, and plus another constant, this is n minus 1 over 2, and HG. So this R is scalar curvature, and H is the unit curvature. So these are the special case when gamma equal to 1 and when gamma equal to 1/2. Okay, so looking at the result of Caffarelli and Silvestro, one first wonder if there is corresponding boundary value problem defined on the manifold. Xn plus 1 with Mn as a boundary, and this fractional operator P2 gamma occurs as a boundary operator. And then the second work is here we have the existence for all 2 gamma between n and 0 that seem to suggest the method in conformal geometry one can extend the result even by the classical result, Caffarelli and Silvestro, to other gamma. Okay, for other gamma. So today I'm going to talk about this aspect. Okay, so first, a different way, say, to identify this on R, it turns out another way to look at the result to see this result of Caffarelli and Silvestro theorem is on Rn plus 1 plus Rn, and then the flat operator, flat metric. Instead of looking that way, we think about hyperbolic metric defined on Rn plus 1. Looking on hyperbolic metric. In that case, so this is the standard Poincare hyperbolic metric. So to view that way, we first notice this Laplace A in xy u equal to 0 with respect to flat metric. We can look at a conformal transformation from xy to this hyperbolic metric, because they only differ by this conformal factor. So if you use that conformal covariant property for this 2 operator, you can rewrite this. When we rewrite this, and then we notice if u is equal to y to the s minus m times u, I'm going to say what's that s. Then this is equivalent of writing this as gh of u minus s n minus s u equal to 0. Okay, and where you remember A is 1 minus 2 gamma, and it turns out this S is n over 2 plus gamma. Okay, if we use substituting this u and use conformal transformation rule, we rewrite this equation into this equation. And so, for example, these are equivalent. I call this Laplace star S operator. So, for example, when A is equal to 0 or gamma equal to 1/2, this Laplace u equal to 0 means the conformal Laplace u minus n squared minus 1 over 4 u equal to 0. And in that case, this is nothing but equal to the P2 of GH and U. So these two are the same. Okay, just using different this. And what's the this is this scalar curvature of this G hyperbolic metric. And what's the advantage of doing so? And that reminds us that in a paper, in the meanwhile, there is a paper by Graham and M.Zworski. And what they did is they began to study a class of manifold called conformal compact Einstein manifold and rederive the existence of GJMS operator in this setting as boundary operator in this setting. Okay, so they derive GJMS operator from the scattering theory point of view on a class of conformal compact Einstein manifold. The conformal infinity of X, boundary X, and then G plus manifold setting. So this is our M boundary. Okay, so they rederive the existence of this conformal covariant operator in this special setting, and where G plus is a class of metric satisfied VCG plus equal to minus NG plus. we actually derived this from a larger class of manifold called asymptotic hyperbolic manifold. But for this lecture, let me say that we think about this as a class of manifold which satisfy this existence of Poincare-Einstein metric. So that they derive this. And then one wonder they use scattering theory. And so let me briefly describe what is going on. So we say that this manifold such class is called conformal compact Einstein space. If there exists a function rho, and which is a defining function on xn plus 1, so rho is positive on xn plus 1, rho equal to 0 on x, on boundary x, and then we usually require gradient rho not vanishing on boundary x. This is called defining function. And if there exists such that rho square of this G plus is compact. Okay. So in general, this hyperbolic metric, Poincare-Einstein metric, is not compact. For multiplying by this rho square, it is compact. So we call it conformally compact. The Einstein refer to say we start with the metric which is Einstein. Okay, so we have this conformal compact Einstein manifold. And one hidden fact I didn't mention is Einstein manifold. This CCE, we call it CCE manifold, but is already asymptotic hyperbolic with sectional curvature on the boundary of the x tends to -1. Okay, and there will be what they did, Brown and M.Zworski did, is they look at the solution of minus or minus s u equal to 0. Okay, I call this conformal infinity. This boundary M conformal infinity because once rho exists, you can multiply rho by any other positive function, and it still is a defining function. So this rho is defined up to a conformal class of metric. So that means this boundary metric is a conformal infinity of this manifold. And what Brown and M.Zworski did is they studied the existence of solution of this function, and this is the eigenfunction. So they studied that for those S where this PDE has a solution, lambda, which has a solution, and saying that with solution you say, let me say that boundary. And so when is this solvable? And then they study the behavior of this function near conformal infinity. Asymptotic behavior of this near conformal infinity. And now let me mention an important work of Mazzero and Melrose. which says that for asymptotic hyperbolic manifold, in particular for CCE manifold, except for finite many of lambda, the point spectrum except for finite many of lambda in 0 to n squared over 4, the solution is solvable. There is a point spectrum, the essential spectrum, but the point spectrum there is only finite many. This is solvable. Solvable. Okay, so that's an important. There is a no point spectrum in no spectrum. So this uses this pseudo differential calculus and study of resultant operator to solve. And now, so except for finite many of this, we can solve this equation. And let me mention some property of this operator solution without really proving it. Some key property. Of solution of this equation. So what they say is, on this setting, suppose you have this defining function. First, some key property. First, there is a property, some fact, which I will assume without use, and that is once this CCE, you have a row where this function is, this metric is compact, and then given H, which is rho square G plus is 3 to the boundary, then any given any representative H in the conformal class, I'm sorry, I'm using the same symbol. So this means this H and that H may differ by a positive function. Given any row, there exists some specific defining function. It's called geodesic defining function. Rho, okay, so rho theta. And this is also a specific defining function, and rho theta with 3 to the boundary is your given H. So given H, there exists a rho theta, and with the special property, the distance function, the gradient with respect to rho theta of rho theta is actually equal to 1 on asymptotic neighborhood plus 0 epsilon. So there exists epsilon positive and defining function such that this is true. So that means in a conformal infinity here, you have a function, and this function with respect to this rho theta square G plus is the honest distance function with a product structure of this boundary cross ellipse. Okay, so this is the existence result. And this is, for example, proof in the paper by Robin Brown. And using, so from now on, I will frequently use this geodesic defining function, and I will give an example of such geodesic defining function later. Okay, so using this geodesic defining function, the property of the solution of
right bigger?
Okay, sure, yes. Okay, So look at solution of this star S. This I have only one PDE, and that's a star PDE. And if lambda is not in the point spectrum, so this lambda is S n minus S. If this is this thing, and then what we have is for each function f in C infinity on the boundary, we have a solution U. We satisfy this equation, and this solution U has two asymptotic solutions. One is rho, and rho is the geodesic defining function.
Can you write larger?
Okay. Rho ns times f plus rho s times h g. Okay, so let me write down this f restrict to the boundary is the given f. Okay, and in general, this f, capital F, starts with f, and the important thing is the next order thing and so on, given this geodesic coordinate, is only has even power of f. Even power. And then up to the order 2k, what is that k? That k is such that this rho plus s, rho minus s plus 2k is less than s. Okay, so I'm sorry, let me start with real s greater than n over 2, so that n minus s is less than s. So I write my function as this function. So this f on boundary rho equal to 0 is the given f. And then what is that g? Okay. And that g is the function which starts with the function k and plus k2 rho squared and so on. Even power of rho. And this k is what we call scattering metric. Okay, this is the scattering metric, k. So k, this k. This is the scattering matrix. Definition of scattering matrix is S on S operating on F is this G restrict to the boundary. And this S is n over 2 plus gamma. And so that's the scattering metric. So if so that's a definition of this. So you will have this. This all comes from the expansion of Melrose and zero, and then one can write this as asymptotic solution, and then due to the resolution of this resolvable operator, we have this term. So G is, this is my K, my notation. So the thing is that this, if gamma, so that's definition of the scattering metric, and it is known. And even in the case of model case hyperbolic metric, in the early stage, it's proved that this scattering operator is a pseudo-differential operator of leading symbol to gamma. Here I should say S cannot be integer. S equals to gamma, gamma not integer. This symbol of S is of order, is a pseudo-differential operator of leading symbol gamma. Leading symbol of order to gamma. Okay, so for example, this when F is equal to 1, then later on we will see that this instance when S is equal to n/2 plus gamma, we define P2 gamma F is equal to this S n/2 plus gamma. So that's a pseudo-differential operator of leading symbol minus or plus to the gamma part. So that's the link between this approach to the comparability sequential setting.
Can I ask,
What?
for this G here, is the powers, the even powers starting points?
Yeah, there's a K, and then it's K2 in terms of K, and powers is expansion, even mode.
Is it infinite series?
Yes.
Oh,
There's under assumption the boundary is real analytic, metric is real analytic, you have power series expansion.
all right, thank you.
Okay. And now let me say that this is when gamma is not an integer. And the link to the GJMS operator, the classical GJMS operator is when gamma is an integer, this is the P2K operator we are making. Okay, so when gamma is an integer, it turns out it's a scattering operator has a simple form. And S equal to n/2 plus K. Say gamma equal to K. The integer. Okay, I don't want to confuse with the other K, but this is an integer. And in that case, it's P2KF. P2KF is equal to the residue of S, the S equal to n/2 plus S. Operating on that. Okay. So at the integer you have Paul, and then the P2, this is the classical GJMS operator. And the conformal covariant property comes from the specific reason this row is chosen up to conformal class. using that invariance, you can see this is a conformal covariant operator. Okay. And so, given this analogy, what in the early days, in early time, Mark Gonzalez and I tried to link the result of this GJMS existence to the boundary operator, the analog of work of Cafarelli and Silvestro. So we have a theorem, that's the Gonzalez, Ma and I. Okay. So we study on this CC setting. We study this as a solution of this thing. Okay. And then we use conformal transformation to look at the G bar equal to rho square of G plus. And this is stated, this equation is stated in terms of the scattering operator. And we look at what is the corresponding thing in this conformal change. And then this is equivalent to divergence of G bar of rho to the eighth power u and plus some potential function E rho AU equal to 0. So this u is equal to this M minus SC. So we play the analog of Cafarelli and Silvestro. So one using this concrete Einstein metric, the other using this compact metric. So, and the advantage of that now is we can try, and there's a potential function which can be explicitly written down, rho of A. And in a special case, of G equal to hyperbolic metric, and rho is equal to y, this E of rho y is equal to 0. And this has the advantage, this is true for all A. Okay, for all A and for all S. So this is specific, but my notation is this is 1 minus 2 times. So we notice that we recover the second of Cafarelli and Silvestro. And then we wonder, can we now begin to write down the boundary behavior of this scattering metric using this conformal change? And then, of course, one can do that. And the little advantage is now this formula holds for all gamma. Okay. So let me first say, in order to cancel out this E rho A term, there is the following observation. So here is a lemma.
There's a question, Alex.
Excuse me, may I ask a question, please?
Yes.
Yeah. Is the full gradient of rho different from 0 at the boundary, or we impose the normal?
E rho A is a function defined on the whole space, xn plus 1. It's a potential function. One can write the expression down.
Yeah.
It involves the scalar curvature of the G bar metric.
No, I mean, even before in the definition of rho, of the defining function.
Yes.
Rho.
This rho is the geodesic defining function.
Yeah, is it the full gradient different from 0 at the boundary in the definition of conformally compact Einstein?
I'm sorry,
Yes.
I don't understand.
Yes.
Yes.
So here we do have,
It's nowhere zero.
It's
No,
never
zero
zero.
on boundary.
The row is
Nowhere
equal
zero.
to 0 on the boundary.
Okay.
Like y is equal to 0 in the upper half space.
Okay, thanks.
This is a PDE where I haven't described the boundary behavior. I'm just saying the interior PDE decision. And now the following lemma. And Ma and I already wondered if there is a further choice of row to cancel out that potential term. And it turns out it is indeed so. So let me say a lemma. This lemma was later specifically write down by Case and I. And what we did is we noticed that if lambda 1 of this Laplace operator is greater than n squared over 4 minus gamma squared, if this is true, and if f is positive. Okay, so you have this U, there's this Dirichlet data, which is U is equal to this function Dirichlet data f. If this f is positive, then the function with then the U of solution of star is strictly positive. On xn plus 1. So this is a simple lemma, and that is because you start with an f which is positive, and then you look at the behavior. The next term is f squared rho squared. So when rho is very small, this function, capital F, will stay positive. And then the other term, rho SG, is higher order term. So in a small neighborhood of rho, very small, this U stay positive. But this compact, this Einstein metric, the only part is non-compact. Non-compact is near asymptotic behavior. And so if for this part, this function U stays positive, you can use this usual operator, this eigenvalue problem for compact manifold to see U stays positive. So there is a little bit proof, but I will skip. By the way, I'm willing to share my notes, and in my notes, I have written down all the details. Okay, so this U is positive. So in particular, it is convenient to choose f equal to 1. Okay, and for f equal to 1, this function we call the solution Vs. I just want a little bit different from the U. A solution V with Dirichlet data 1. Then this Vs is positive under this assumption. Positive. And then one thing one notice is that means one can define a metric rho S to be 1 over n minus S power. This function is well defined. This V is like U, start with rho to the n minus S power, capital F is 1. So if you take to the 1 over n minus S power, this function rho S, the leading power is the same as that geodesic defining function rho. So this is a function whose behavior, boundary behavior, is the same as my function. The advantage of this function is this function has E rho S of this A is equal to 0. Okay, one check that. Okay, so that means when I use this conformal transformation, I'm getting into the same with respect to this metric. We are getting into the same thing. This in compact manifold, we get to this Laplace A operator, which is rho to the eighth power diversion G bar rho AU. Okay, so we have the analogous problem as this. So I call this the metric. I call it this is the adaptive metric. Just give it a name. These are the specific solution with this Dirichlet data F identical. And now I will give some example describing property of this adapted metric. Okay. So before that, let me say that using this metric, we now have the following setting of Paparetti-Silvestro theorem in a CCE setting. So for example, so using this, we have, say, on flat setting, we call the P2 gamma F is just a YA DYU, and limit Y tends to 0, up to constant. But on this CCE setting, this P2 gamma F, in this case, is equal to some constant, and then limit rho star tends to 0, and rho star A, A's power, and D rho star U. And then it turns out, since we are in flat manifold, there is this equal to, there is F and then Q2 gamma operator. And where is a P2 gamma is P2 gamma operating on the function F equal to 1. So on the flat setting is Q2 gamma is equal to 0. And we have this fractional curvature Q2 gamma, which comes from this. And this is for gamma between 1 and 0. But this formula can be expanded to all gamma between n/2 to 0. With an expression a little bit complicated, I will write it down when I describe the examples. Okay. And now in the rest of the talk, I like to give example of adapted metric and to say that to view this way, what are the advantages? So here are the examples. So it turns out the first important example is when S is equal to n plus 1. Okay. And when S is equal to n plus 1, this is a setting this result is, so we are looking at this equation, Poisson equation, this equation minus Laplace S equal to n plus 1. Then we are looking at solution S times n minus S, now is minus 1. So my minus cancel. So we are looking at solution of this guy. And with the Dirichlet data, F equal to 1. So we are looking at this solution with respect to this hyperbolic metric. This is a metric, Einstein metric. And now there's a theorem of Lie, important theorem of Lie. Remember, for this equation to be, this metric to be defined, we have this condition. We want lambda 1 to be n squared minus, now avoid greater than this number. And on the other hand, the general theorem tells us between 0 to n squared over 4, there may be finite many things where this number could be point spectral. So we want to avoid that, and this is the result of Jack Lie. Jack Lie say on CC setting, so this is the old result in 95. On CC setting, if the scalar curvature of the boundary metric is positive, this is an assumption, then they say that, this is a boundary of X, then the theorem say lambda 1 of minus plus is actually greater than p squared over 4. In other words, there's no point spectrum. No point spectrum. Okay. So what's the connection of this to this? It turns out these proofs use solution of this Poisson equation at the index S equal to n plus 1. So let me first say a few words about the idea in the proof of B. So this is the idea strategy of proof. The strategy of proof is to say, to show, first, observe, to show lambda 1 of any operator is greater than, say, this number, it is enough to find some function phi positive of xn plus 1, and which satisfy minus Laplace plus minus n squared over 4. Phi is positive. It is enough. The first observation is this. Proof, once one have this, then if there is an eigenvalue Laplace psi equal to n squared over psi, and then you can use comparison principle to show lambda 1 is greater than n squared over 4. So it is enough to show that. But this strategy is to test v equal to v to the minus alpha power. So suppose there is a solution v which has this thing and v is positive. And then his idea is to try to test this. And when you test this, then one sees that this, if v is a solution of that PDE, and we test v to the minus alpha power, then we see that this minus Laplace phi over phi over phi. We want it to be greater than or equal to this, but if phi equal to v to the minus alpha, and the v satisfies that PDE, then let's see that this is tends to n minus alpha. One can use that, show this tends to this number on boundary of X. We know the behavior of V on the boundary, so this part is convincing. And then, in order to establish, in order for this to be which this number is minimized and maximized when alpha equal to n over 2. If we look at real integer. So that means we are testing phi to the minus n over 2 power in order to reach this n squared over 4. And then, in order for this function phi to be positive on this, and we observe this strategy is to show that this function is implied by minus or plus v. I'm sorry. Okay. By Laplace plus v square minus gradient plus v square is positive. Suppose phi is v to this power, then to test that is equivalent to say that. So you are going to say any solution of that PDE Poisson equation has that property, and that's what we show. And then, so his key lemma. The first is he compute the asymptotic behavior of V squared and show it's equal to R scalar curvature on the boundary and plus O rho squared. That's step one. And then, so if this is positive, then we have this Laplace plus phi over phi on the boundary is positive, tends to that positive number. And then the second thing is to show this v squared minus plus v squared is indeed negative. I'm sorry. This turns out to be negative. And so combine 1 and 2. I'm sorry, I'm a little bit lost. Combine 1 and 2. 1 has v squared minus this v squared is greater than this Laplacian is negative. And so that means the minimum is on the boundary of the function, while the minimum is greater than 0. Minimum of RH of boundary, which is positive. So that shows this v squared minus v squared is positive. I'm sorry. So I should say this positive implies this positive. The reason why this is positive from X follows from 2. Okay, so we establish 2 relations. One is the asymptotic behavior, which is not surprising because we know the asymptotic behavior of V. So it's a direct computation. The second thing is surprising. He computed this and showed this is negative, and then maximum principle say this function is positive. Okay. And now, let me say, so this is the theorem of Jack B. But later on, Qing also made an observation, further observation of what Qing observed is this quantity computed bijectly are geometric quantity. So what he observed is if the matrix, so notice that this V is rho to the -1, rho to the n minus s, and then this s is n plus 1, so this is rho minus 1 plus asymptotic behavior. So the matrix G star is V to the -2 G plus. You want to have a compact manifold with V minus. So Qing's observation is V square, this quantity V square is actually by conformal transformation between G star and G, this is actually equal to the scalar curvature of G star. Okay. So this property 1 implies the scalar curvature of G star is positive. So a corollary of Jack-Lee's theorem result is that if the boundary Yamabe scalar curvature is positive, would imply in the interior of the manifold, CCE manifold, there exists symmetric whose scalar curvature is pointwise positive. And so there exists G star in this conformal class with scalar curvature of G star is positive. And another way of stating this theorem is an equivalent way of stating this theorem is to say if the boundary Yamabe constant is positive, strictly positive, that would imply on the CCE setting, the Yamabe constant on the interior of this metric is positive. Okay. But on the other hand, we only get a conclusion is greater than equal to 0 because at this moment, remember the Yamabe constant has the integration of the scalar curvature volume, d volume, and normalized by the volume. And we do not have control of the volume of this metric yet. So we only can conclude it's greater than equal to 0.
So there are no
And
counters
this,
yet.
yes,
There are counters.
I will return to this later. I'll return to this later. Okay. So this is a corollary of this. And then the other thing is, it turns out, so this is 1. And it turns out the reason why this V square minus is positive. If one sees that, and one directly using Buckner formula to compute, it turns out this is minus V of the Hessian metric minus V of Gij plus square. That's the reason why it is negative. But compare this to the metric G star. This metric is minus 2 to the n minus 1 square, and then the traceless receipt of G star square. Okay, so this metric means this metric has Laplace of G plus of scalar curvature of this metric G star is equal to minus some constant times this G squared. Okay. So So hence, by maximum principle, scalar curvature of G on the boundary is positive. So and it satisfies this PDE. So that's the geometric content of this Jacques theorem. And it turns out this is a special example, and this turns out to be common property of a large class of adapted metric, which I'm going to describe. So this is a first example, is Jack Lee example. We look at the index S equal to n plus 1, and then we have the theorem. And now let me describe a certain example. So the second example, we try to understand gamma between 1 and 0. So let me first say a pattern from gamma is equal to 1 half. So if we look at this star equation, I only look at one equation. So in that case, S minus n minus S is n squared minus 1 over 4. We look at this specific index, and as I say, this is the same as equal to T2 of G plus T is equal to 0. And now, let me say, describe some property of this operator, of this example. So the properties, in this case, this metric is G star metric. There's always specific index, but that we not write down. This S equal to n plus 1 or 2. Okay. So the property of this metric, the first property is this is satisfy the scalar curvature of G star is 0. That's by conformal law between G star and G plus. Okay, so by conformal transformation law, you know what's the scalar curvature of G plus. It's this. So this is equal to 0. So that's the first property. And then there's an important property which we rely heavily later on is it turns out that the scalar curvature on the boundary is positive. If we assume that this condition in the Jacques metric has scalar curvature on the interior positive, but on the other hand, for this specific index, we only have scalar curvature positive, but we have H, the mean curvature is positive. On the boundary. Okay. So let me say a few words why this is the case. So there are two ways to see this problem. Two, follows from a result of CHANG where they say that if the boundary metric is positive, they study this we call scattering pole. The scattering pole of the scattering metric, and a corollary of that is Q2 gamma is positive for each gamma between 1 and 2. Okay, this fractional Q is positive. So in particular, when gamma equal to 1, when gamma equal to 1/2, gamma 1 is the mean curvature. Okay, there may be some constant, and that constant actually is a negative constant. So let me be careful. This is H, and depending on dimension. But that constant is sometimes negative. So this is it. So H is positive. But one can also an alternative proof. Is the following. And we can use conformal transformation rule of mean curvature. We can interpolate between this metric GL, which is obtained when S equal to n plus 1 to this G star metric, and S equal to n over 2 plus 1. We can interpolate this, and that is and for this, for GL, the Jack-Lee metric, it turns out this Jack-Lee metric, because it starts with S equal to n plus 1, one can see that the next F1 is 0, so it starts with F2, so this H for L is 0. The mean curvature of the Jack-Lee metric is 0. And also, actually, GL is totally geodesic. Okay, so I don't want to get into detail. It turns out all CCE metric boundary metric of CCE manifold are umbilic. Umbilic means the second fundamental form is times is a portion of its metric on a boundary. And the reason why it is all umbilic is because using geodesic defining function to look at a metric, that's umbilic, and the umbilic is a conformal invariant property. So all metric, which is the boundary metric in this CCE setting, are all umbilic. So to show it's totally geodesic, that means you want this mu to be 0 here. You only need to check its mean value. When its mean value is 0, it's totally geodesic. Okay, and then we look at the conformal transformation law between this HL and our G star metric, and then one can write down the PDE. So I'm getting a little bit into detail, and that is, so you write this G star metric into U square GL. U square GL. So what is then U square of the mean curvature G star is equal to U times G H of GL and then plus du d normal. That's the conformal transformation law between two conformal metric if it's U squared. So, and now you have this is equal to 0. So to show this H is positive, amount to show this solution, U has DU normal positive. But that you can do because then you can show by looking at we know this metric has scalar curvature equal to 0. And use this conformal transformation law again. This would imply that this LGL imply this LGL on this U to the D minus 2 over 2 is 0. D is, I'm sorry, is my N plus 1. Okay. So, and from there, you can see this means that this U D minus 2 over 2 is less than equal to 1 on boundary on X. U, here I have this U can be written in terms of the GL transform and in terms of this GL. There's a bit of detail which is here. And so, and then this implies U on the boundary is 1. So, and it's in the interior by this law will be less than equal to 1. And so that means DU D normal has a sum. Okay. Whatever it is, your sum. I'm sorry, I'm a little bit confused about the sign now here. I want it to be positive, somehow this is negative. There's a sign problem. Maybe this is the outer normal, and that's inner normal. Okay. Okay. So that's the second property. Let me finish with the third property, and then I will summarize and continue tomorrow. A third property of this S equal to 1 plus 1 a geodesic metric is the gradient of G star of rho star is less than equal to 1. And this property actually comes from, this property was proved by Fan Wang, and the proof is non-trivial. But later on, we can understand that he proved better. If you look at the rho, this function 1 minus gradient G rho squared. And why should one look at this? It's not entirely clear. And D on the boundary turns out about 2/3 H. And then she applied maximum principle on this metric and show it's negative. And this implies D is greater than equal to 0 on X, and which transfer to the property with 1. So there's so consider this and then compute this and then so on. But I will come back to this step later. It turns out there's a geometric reason why one should consider this quantity, which I will explain tomorrow. Okay, and now let me remark, do I use all my time?
You started 5 minutes later, so.
Oh, okay, so now let me remark that this metric is not, no. This metric is not escobar. Metric for boundary are not important. what is the Escobar boundary and multi-problem? Escobar say there is a space Y, let me not use X, not to confuse myself, with a boundary of compact setting. Escobar says under conditions you can find there exists a metric with a scalar curvature of G is equal to 0 on Y, and then this mean curvature is equal to constant on boundary of Y. Okay. Our metric has scalar curvature equal to 0 on the interior, and we only know its mean curvature on the boundary is positive. Then one thing, why the existence, why doesn't use this metric instead of this special metric comes from Poisson scattering theory? The problem is this Escobar's metric, when we restrict it to the boundary, we do not know what is the behavior of G on the boundary. The problem is behavior of this metric G, let me say Escobar metric on the boundary is known. Okay, we only know its scalar curvature is 0, and then we do not really know. And for our metric restrict to the boundary is a given metric, so it's a dirichlet problem. We start with the boundary metric, we build up inside. So those are the difference of the two metrics. And ours is a boundary value problem. This is an existence problem. So I will continue tomorrow, and tomorrow I plan to give another example describing this adapted metric for gamma between 1 and 0. And then I want to talk about what happens when gamma is bigger than 1. Okay. And where it's the Chemnitz operator and fourth order PDE comes in. So I will discuss that.
Questions?
Alice, when you have clear that the scalar curvature positive implies that the fractional curvature is going to be positive. So there, in the King-Guillermont result, you arrive to the Q curvature is between the gamma is between 0 and 1. So you arrive to the scalar curvature. So for you, Q2 means scalar curvature, right? Q to gamma, when you have Q2, is the scalar one.
Oh, Q2 is a scalar curvature.
It is scalar curvature. So, do you know or do you expect that it also goes in the same way as Q2 inside?
Yes, I know that Rafe and many people have worked trying to pass this theorem for gamma beyond 1. There is partial result, and also it has something to do with the Hausdorff dimension of it's another domain. Okay, there is partial result.
Okay.
One try to interpret. For example, one try to say it's 2 plus positive. And then there is a stable curvature on the boundary is equal to 2. And suppose these all are positive. Do we have in the middle thing is positive? I think it's only very partially.
Very partial, okay. But do you expect that?
Yes, Rubin Zhang also has worked in that direction.
Okay.
Yes. So long the interpolating is only here. And then if you are passing, then I know there is only limited partial result.
Thank you very much.
Yeah.
I have a question. So with the conformal infinity is fixed, but the inside is maybe different. What happens about when gamma is equal to 1/2?
What is each have its own extension?
The operator is different, but
Okay.
what about the spectrum?
Okay, there is this Hawking page example, such that the conformal infinity is the same, but we know the internal extension is different. So for that, you have two different conformal Einstein metric. I suspect your P1 is also different, but I haven't seen the proof. One knows there are different extensions. Does that mean there is different pseudo-differential operator? I don't know. Does that answer your question? So this extension, given a G plus, that exists, but you don't know if there are two different extensions, these pseudo-differential operators are different, even if the conformal infinity is the same. Sure. Yeah.
As you point out, as integer, the residues you independently fill in.
Yeah. That's a differential operator. It's only depending on the boundary metric. It's not a local thing. Yeah, at those integer point, it only depending on the boundary metric. You are right.